Well, welcome back to the Introduction to Radar Systems course. We're now working on the propagation effects lecture, and we're going to start part 2 of that lecture. Okay, at the end of the last lecture, we went over basic interference effects. Let me just take it a step back further. Okay, here we are with the outline. We're discussing reflection from the Earth's surface. At the end of the last lecture, we discussed basic interference issues. We saw that two waves can constructively or destructively interfere, and this can result in quite different relative amplitudes of the sum, depending on how the phases are, the relative phase of wave 1 and wave 2. The voltages can range from 0 to 2, these voltages squared, which are the power, 0 to 4, and because the interference operates on both the incoming and outgoing wave, it can be a factor of 16. And now we'll move on to the first view graph of this part. We're going to take that concept of interference and look at the practical example of propagation from a radar to a target and back over a plane Earth. That's over a flat Earth. Now the reflection from the Earth's surface will result from the interference of the radar signal that goes directly out, hits the target, and comes back. And if the beam is sufficiently broad, as it would be in a low-frequency beam, some of the radiation will go out at a slightly lower angle, will reflect off the Earth, go up, hit the target, and reflect back. And it's the interference of those two paths, the direct path and the multipath, that we're going to examine. Okay? Now, we notice we've got a reflection off the Earth. That's characterized by a surface reflection coefficient, which determines the relative amplitude of the reflected signal. Now that reflection depends on the surface of the Earth. Is it a very shiny surface, like we'd say that ocean is mirror smooth? Or it could be a very rough ocean. Or if it's land, is it quite absorbent? And so the reflection coefficient for rough land could be close to 0. For a smooth ocean, it could be 1. It also depends on the polarization of the radiation going out and on the frequency. Now, if you have a smooth ocean, there's going to be a change in phase at the reflection. So there'll be a 180-degree shift of the beam as it reflects off the ocean. And so this capital gamma, the reflection coefficient would be -1 at that point on a very smooth surface like the ocean. So the relative phase that we want to look at between the direct path and the multipath is dependent upon the path length difference and the phase shift on reflection. And in turn, these are dependent on the geometry, which are the height, the range, and also the frequency of the radar, which will tell us how many wavelengths are different between one and another. Okay. Now what's going to happen is that there's going to be a set of times when the two paths, the direct path and the multipath, will interfere constructively and destructively. And as you look at the angle of the multipath beam as it goes down, you'll go through the minima and maxima. And so this multipath effect, the addition of the direct path and the multipath, causes the elevation coverage to break into what we call a lobed structure. There'll be elevation angles where we'll have greatly enhanced detection performance and reduced reduced detection performance. A target located at the maximum out here, since the difference in the two paths can be 16 times. You're over a smooth ocean, That distance, the power difference, taking into account both the way out and the way back, can be 16 times difference, which would exactly double the range. So here's a line of target altitude as a function of range. If there was zero reflectivity, zero reflection of the multipath, and that would be the normal range of the radar, and it can double if we have multipath that's very strong with a very smooth surface. In between, if we have a reflection coefficient that's moderate, say 0.3, which would be a slightly rough ocean or a medium rough ocean, something like that, then you'll get reduced range, but these minima won't go to zero. They'll go, the detection range will go down, but not to zero. Okay? So you can detect farther and less. Okay. Now let's look at what happens when we change the frequency. If we just change the frequency, the path length difference will be double if we double the frequency, because there'll be two whole cycles in that same path length. And that would mean we'll go through a minimum and a maximum twice. And so we'll have two lobes at double the frequency and the same elevation coverage where we would have one at, say, the first frequency. And again, if we halved the frequency, our lowest lobe would be between the first and second one here. So notice one performance issue that comes up. If we're very interested in detecting low-altitude aircraft, the bottom of our detection beam is going to go up, and we're going to have poorer coverage when we go to lower frequencies, but we'll have more lobes. An interesting exercise for the student would be to look and to see for the geometry as we had before, say an aircraft at 500 feet above flat sea level and a radar at 100 feet, and you were dealing with a range to the radar of, say, 10 nautical miles. Say, if I were at X band, 10 gigahertz, 3 centimeters, how much frequency shift would I have to give to go from a minima to a maxima? In other words, as I was operating the radar, could I go from one frequency to another to fill in these lobes and still get pretty good low elevation coverage? It's a good student. If there are any students in the audience that have some science or electrical engineering background, that's a good exercise for you to do. But the main point is that the lobing density increases with increasing radar frequency. Now let's look at over-the-horizon diffraction. First I want to go over the whole concept of diffraction of waves. Now there are a couple of different physically intuitive, the mathematics can get a little gory at times, but there are physically intuitive examples that one can give to show you that. The first one is this set of 3 photographs. They're time-lapse photographs of a simulation of a tsunami wave. And this area in the greenish-brown is the land, and of course the bluish area is the ocean. And these scientists at the NOAA have simulated coming in from the left a tsunami that's about to strike this peninsula. And in the center you can see the tsunami wave is interacting with the peninsula. Some of the energy is reflected back and some forward. And then after a little time later, you notice that waves have bent around the peninsula and are coming into the land. The ocean wave diffracted around the land. So these waves don't just move in a strict line of sight. We're used intuitively with our eyes to very, very short wavelengths. And it was so-called geometrical optics, very short wavelengths. And the light, as we see it, at the wavelengths we see it, doesn't go around corners. It just goes in straight lines. And at the distances we're normally looking at with our eyes and the sizes of edges, we don't see that diffraction. It's not obvious to us in our intuitive way of looking at things. Another simple example, and I was thinking, say you were in a lecture hall, and you were near the back of the lecture hall, and you look directly at the lecturer. You can hear the lecturer quite well, and you can see the lecturer. Now you back up to the doorway, and the door is wide open. It's a big set of double doors. You're in the doorway. You look at the lecturer, and you can see the lecturer. Now you'd back up 5 or 6 steps beyond the doorway, and you can still hear the lecturer. Now if you move to the side so that the wall is in your way of the doorway, you're not in the doorway so you can see the lecturer, but you've moved just sideways, you hear the lecturer but diminished. So those sound waves are traveling around so that you hear them. That's an example of diffraction. There are 2 other excellent examples for copyright reasons. I couldn't put them on this open website. But if you go to these 2 URLs, you'll see 2 beautiful examples of water waves coming into a breakwater and diffracting around it, and water waves coming in to a landmass and clearly diffracting around the landmass. Actual photographs of water waves. So the ability, in the final bottom line, the ability of radar to propagate beyond the horizon, I want to point out, it depends upon the frequency of the radiation. It turns out the lower the frequency, the easier it is to propagate around, and upon the height of the radar, so that you have better line of sight over the particular obstacle, whether it's a tall hill, a mountain, or the normal horizon of a regular flat Earth. Now let's look at some geometry to put into perspective what we're looking at. The area that we talked about on a curved Earth, between the radar and the tangent ray to the horizon, between what we call the line of sight path from here to the horizon, we call that the interference region, all this area, and that's because we can have a direct path going up to a target, and it's the area above the line of sight. Okay, we can have a target up here too, and it can bounce back down for the multipath and go straight. But the area below that tangent ray, from the radar to the line of sight, we call the diffraction region. And signals below that diffraction region, within that diffraction region, are severely attenuated. But there is some detection. Later on, when we have a lecture on radar cross-section issues, there are some simulations of electromagnetic waves coming over a barrier. And there's a beautiful simulation of how the electromagnetic wave bends around a barrier, and I'll point that out to you in that lecture also. Okay, now we're going to look at the effects of diffraction and multipath and how they depend on radar frequency selection. Here we have a radar that's at a 100-foot altitude, and here is the 100-foot altitude following the curved Earth at 60 kilometers. And we're looking at an L-band radar. Here we see the lowest multipath lobe we've plotted at L-band, and the lowest multipath lobe is plotted also at X-band. Out at 60 kilometers, the loss is 60 dB, diffraction loss, because we're below the horizon at L-band, and the loss is 80 dB at X-band. Okay, so you can see from a diffraction point of view, it says you'd rather be at L-band. But if we look above the geometric horizon where the aircraft would be, the X-band lower beam has better low altitude coverage. So we note that a low altitude multipath detection favors the higher frequency, X-band, over lower frequency. But for diffraction detection, below the geometric horizon, it favors lower frequencies like L-band, but it's tough at any frequency because those are very significant losses that the radar would occur. Now on to atmospheric refraction effects. Refraction is that principle where the physical principle where when there's a change in the index of refraction of the medium, that an electromagnetic wave, and in our case microwave radiation, which is electromagnetic radiation, it's when the radar beam passes through a medium where there's a changing index of refraction, then the radar beam will bend. Now, I just said the word index of refraction. And the index of refraction is the ratio of the speed of the electromagnetic wave in a vacuum to the speed of the electromagnetic wave in the medium. Now, what does that index of refraction depend upon? It depends upon the temperature of the atmosphere, the pressure of the atmosphere, and the partial pressure of the water in the atmosphere. And that index of refraction drops off with altitude. It drops off exponentially in a mathematical sense. The index of refraction at the Earth's surface is very close to the vacuum, but it's that in the vacuum, but it's not. It's 1.000350. 350 parts per million away from just being what the index of refraction would be in a vacuum. Okay? But that 350 parts per million, which we call that the number of parts per million, we call the refractivity, and that drops off in a normal atmosphere about 40 parts per million, sometimes as low as 25, sometimes as high as 75 for a normal atmosphere, that many parts per million per kilometer of height. Okay? And we call it super refraction. That's a lot more bending if it drops off, say 100 parts per million. If it's over 160 parts per million that it drops off per kilometer, we call that super refraction. And we'll see shortly, then the beam can bend a lot, an awful lot. Now let's look at this this view graph in two parts to understand refraction. Just refresh your mind. Here we have two pens in glasses. The one on the right, the glass is empty. So between the pen and the camera, so to speak, your eye, there's just a thin layer of glass which doesn't do anything. It's hard to see the effect, but there is a slight effect. So there's no really big chunk with a different index of refraction than air. You see the pen, and the light moves from the pen to your eye or the camera in a straight line. But we fill the glass with water, the light bends at the interface between the water and the outside, the air between you and the glass. And that bending gives rise to an apparent different location of the pen inside the water. And that's, you can visibly see, that's refraction taking place right there. Okay? Now that's between a water-air interface. Now let's look at this view graph above to examine what happens when a radar beam goes through either with or without refraction, travels across the Earth. The radar ray, in the absence of refraction, would move in a straight line. Okay? If the index of refraction were constant with height, just move in a straight line. But since the index of refraction varies with height, the radar beam is bent and the radar horizon is extended further away. So the radar can see further away than it could if the index of refraction did not change with height. Now let's see what that means in terms of how we do calculations and things. Now you could see from the previous view graph that the distance you can see depends on how curved the Earth is. Okay? Now, if the radius of the Earth were greater, you could see farther. So, but what we can do is to account for the refraction by replacing the Earth in our geometrical calculations, replacing the radius of the Earth, A, in those calculations by an equivalent Earth radius, Ka, and then assume straight line propagation. So here we have an antenna beam bent due to refraction by the Earth's atmosphere, radius A, and the shape of the beam in an equivalent Earth represented with a radius Ka. Okay, and it will give you the same results for the radar horizon. Typical value for K for a normal atmosphere is 4/3, and we refer to that as 4/3 Earth propagation. Okay. Now, with that 4/3 Earth propagation, the normal atmosphere, we have the radar beam going in a straight line, propagating in a straight line. If we have less of a decrease in refractivity than that typical 40 parts per million per kilometer, we call that subrefraction, and that limits the radar horizon. But if we have more than that, we call it superrefraction. And then we can have an effect if it goes up to 160 parts per million per kilometer for the decrease in refractivity. Then we call that ducting, and that effectively has the radar beam trapped, going in a very, it just to follow the Earth's horizon is only limited by the attenuation of the beam. Now, what's the effect of ducting on target detection? With no surface duct, the radar would have a number of multipath lobes, and we have two targets that are heading towards this radar, and we see with no surface duct that this aircraft would be detected by the low beam, and this lower aircraft wouldn't be seen till it was much closer into the radar. If we have a surface duct, that lowest beam would be bent down, and the lower beam would be detected, and the upper aircraft, and the upper aircraft would be not detected till much further in. There'd be effectively a hole in the coverage. So you can see that ducting can extend the low altitude detection, but can also cause unexpected holes in the radar coverage. Now here's a plane position indicator, a display of detections above the minimum detectable signal of a radar located in the vicinity of Boston, Massachusetts. You can see in dark solid lines the outlines of the states. Here's Cape Cod, Rhode Island, the eastern part of Connecticut, New Hampshire up here, and Maine. And typically under normal atmospheric propagation, you just see a little bit of ground clutter around the Boston area. You might see a little bit about the hills around Worcester, Massachusetts, in central Massachusetts, but not much else. You would not see any detections from Cape Cod, which is 50 to 100 feet above sea level at the most, out at 100 kilometers. You just wouldn't see it. But here you notice it very nicely. You have a lot of detections at Cape Cod. You even have detections up in Maine. No way would you see that in a normal atmospheric conditions. And these the colorations are in units of dBz, which are used for weather radars to denote intensity of backscatter, of volumetric clutter actually, but they also show up ground clutter. And so what this shows you, I'll just point out these are 50-kilometer range rigs. So we're seeing, clearly in a relatively flat area, ground clutter over 50, 60 miles, and that's really unheard of in the New England area that you'd see ground clutter over such a great area. So ducting conditions can extend to extreme ranges of the horizon. It's the message I'd like to leave you with. So now, to finish the lecture, summarize, we've gone over in the lecture atmospheric attenuation and all the different effects that come into play. Multipath reflection and interference, multipath. We've looked at diffraction, the trade-offs in multipath and diffraction at different frequencies. We looked at refraction, bending of radar beams in the atmosphere, and how under different atmospheric conditions the bending can be slight or extreme, and what those effects would be on a radar. And here are the references, and shortly we'll move on to the next lecture. Thank you.